Hello, my name is Katie, and this is the advanced presentation for the group regarding the Michaelis-Menten equation, and we are to explain and go through the derivation of it. So I'm just going to start by talking about what the Michaelis-Menten equation is. So this equation helps us look deeper into how enzymes behave and help us catalyze reactions within our bodies. This equation helps us study the rates of the enzymes and the rate at which they catalyze reactions for particular concentrations of substrates. In this module, we worked a lot with graphs that showed the reaction velocity when a certain amount of substrate was added until the reaction reached maximum velocity. And the derivation of the Michaelis-Menten equation kind of depicts this process but in formula form. To begin, we start with our enzyme reacting with our substrate, joining together to create the enzyme substrate complex. So I'll go ahead and write that. So for this, we have the enzyme plus the substrate goes forward, K1, into our enzyme substrate complex, and this just indicates that it is a reversible reaction. It just indicates that it can go forward and also backwards. So K1 indicates the forward arrow, which just means that K1 equals E plus S equals ES, and K negative 1 is the backwards arrow, just meaning that this indicates the breaking down of the enzyme substrate complex. So this is ES goes to E plus S, so it just breaks it apart. That is the beginning of it. The second step is where the enzyme substrate complex breaks apart into the enzyme and the product. And this only has one arrow, as there is not enough product created to allow a backwards path to happen. And so the K2 indicates the reaction moving in one direction without the ability to reverse. So this can be written as, let's see, here it is, ES goes forward into E, the enzyme, plus the product, and this is depicted as K2. So K2 equals the forward, and it just cannot reverse. So to solve this equation, we start by making a steady state approximation, just meaning that the creation of the enzyme substrate complex, so ES, is equal to the sum of all reactions decreasing its concentrations, or in other words, K1, or reaction K1, which creates ES, minus K1, which consumes ES, minus K2, which also consumes ES, is all equal to 0. So this can be written as K1 minus K negative 1 minus K2 is set equal to 0. And we can substitute into this equation these variables. So K1 we know is E plus S equals ES, so we can substitute that there. Same thing within the K negative 1 and the K2. So let's see. So this can be rewritten as the instantaneous rate of change of ES over dt, which equals K1 times concentration E times concentration S minus K negative 1 ES minus K2 ES, all equal to 0. So I'll go ahead and write that out. So we have the instantaneous negative change, so d es over dt equals to 0, because we set everything to 0 for this one, and this equals the k1 times e times s minus k negative 1 concentration of es minus k2 es. All right. Yeah. Okay, and then so for this equation, these expressions mirror our methods for initial rates, where the reaction only depends on the concentration of the reactants. So for the issue with this, one of the issues that we have is that it's hard to determine the value of the unbounded enzyme, and to solve for this, we define ET or E total to represent the total concentration of enzymes. ET or E total must then equal the concentration of E, the unbounded enzyme, plus the concentration of ES, or the enzyme substrate complex, the bounded enzyme. And then we can subtract ES from both sides and solve for E. So I will write this out. So we have the concentration of total enzymes equals the concentration of E plus ES, and then we want to, let's see, and we want to solve for E, so then we can write this as concentration of E, putting it on the other side, equals concentration of enzyme total minus the enzyme substrate complex. So now we can substitute the enzyme total for our ES in the previous equation. So this we can write now as the instantaneous rate of change of ES over dt equals K1. And I'm just substituting these values in of enzyme total minus the concentration of ES times concentration of substrate minus K negative 1 times the concentration of ES minus K2 concentration ES. And so after we substitute the values from the previous equation, we get this equation. And now we can set this equation equal to 0, and we will get 0 equals K1, just factoring everything together and kind of smoothing it out. So we have 0 equals K1 times the concentration of E total times the concentration S minus K1, so ES times S minus K negative 1 ES minus K2 times the concentration of ES again. So now our goal is we want to use this equation to solve for the concentration of ES. So we have to get all terms of ES to one side of the equation, and then we can divide, leave ES by itself to, let me just start writing this out. So we have 8. We have to get all of ES on one side. So we have ES times K1 S plus K negative 1 plus K2, and then equal to K1 equals, sorry, a bug just flew in my face, K1 times the concentration of enzyme total over multiplied by S concentration. So once we do that, we can further solve. So we have ES alone, the concentration of ES alone on one side, and this equals K1 times the concentration of enzyme total times concentration of S, and that would be over K1 times concentration of S plus K minus 1 plus K2, and to further solve from here, let's see, we can multiply the numerator and the denominator by 1 over K1. Let's see, this over K1, 1 over K1, and then it will be, we have ES alone on one side. Can you guys see this okay? I hope so. Okay, well, so on this side we now have ES equals E plus the concentration of S. No. Times X over S plus K negative 1 plus K2 over K1. Okay, so that is what we have so far. There. Alright. And so we still have to solve for the instantaneous rate of change for product as a function of its reactants. In other words, we need to solve for velocity. There's only one reactant for the reaction for K2. As you can see here, one reactant. Here. So now we can just substitute the equation for ES into this equation, which would leave us with, we have D instantaneous product over dt, other words known as velocity. And we can equal this to K2 times the concentration of ES. Yes. Further, we can concentration P dt equals K2 E plus concentration S substitute S. Oh, and now we have this. After substituting the equation for ES into this. So next, this leaves us with the Michaelis-Menten equation, which we can rewrite as velocity or d concentration P over dt equals k cat, where k cat just equals k2, and let me have a concentration E plus concentration S over concentration S plus Km. And so K cat is just equal to K2, and we can see that if we multiply that, we just can substitute it. So this is all the same on the top, and then we have the concentration of the substrate plus Km. So Km is just the Michaelis constant, which is this right here. So the Michaelis constant is K-1 plus K2 over K1, which is a lot to write, so we just kind of depict it as Km. So velocity is just another way of saying the reaction rate of the product, or dP over dt. And let's see, K-cap, further talking about K-cat and K2, this is called the turnover number, and the turnover number is the maximum number of molecules of substrate S an enzyme can convert into a product per the catalytic site per unit of time. And this just measures how many molecules an enzyme can work with per second. In the numerator, we have K-cat multiplied by the enzyme total, which just means we have the total concentration of enzymes times the maximum number of molecules an enzyme can catalyze per second. And if we have all of the enzyme reacting with the most molecules possible per second, we have the maximum rate, which is signified by velocity, or otherwise seen as Vmax. This just means that we can substitute the numerator of this equation with Vmax, and so I will write that down. So Vmax equals K2 ES max, otherwise known as Vmax, equals the K2 times enzyme total. And so we can substitute that in, and we get our Michaelis-Menten equation, which is velocity equals velocity max times concentration of substrate over concentration of, let's see, you guys can't see this, concentration of substrate plus the Michaelis constant. Yep, okay, and that is kind of the best way that I could personally explain the derivation of the Michaelis-Menten equation. So I'll just kind of start from there, and we can just scan to here. So as we can see, it's kind of a complicated equation, but it's definitely well worth understanding, because otherwise, yeah, it's well worth understanding. Thanks for watching, and I hope that was as clear as I could make it. Thanks.